Hello guys, in this video we will talk about unbiased estimator of errors variance. When we are constructing a model, we often want to not only know the forecast but also understand the extent of the uncertainty which is associated to this forecast. That would give us an additional information about the modeling process and can influence our decisions. Because if we understand that the error magnitude is high, then we would probably resort to some risk management techniques in order not to be exposed to an excessive risk. And the most common measure of the uncertainty associated with the forecast that we get is the variance. If the variance is big, then it means our forecast is not very accurate. If the variance is small, that means our model is good and we almost perfectly predict the process at interest. That's why it's very important to obtain some kind of an estimator of the errors variance. Why do we call it an estimator? Because we are only working with the sample. We don't have an access to the population. If we could analyze the whole population, then we would probably be able to compute the true variance of errors. But unfortunately, it's never possible. We are just working with the sample. That's why, since we cannot get the true variance of errors, we seek for its best estimator. Take a look at this equation. We can write in a matrix notation that y is equal to xb plus e, what is also equal to x beta plus epsilon. And beta and epsilon in this case are the true parameters and the true residuals, true errors of the model, which we don't know since we are only working with the sample. Then from this expression we can get the analytical form for E that would look like this. You see, E is equal to x times beta minus b plus epsilon. Then, if we consider the analytical form for the parameters vector b derived in the previous video, we have this form x transposed x inverted times x transposed y, and then we simply replace y with this expression, and then we will get x transposed x inverted x transposed times the replaced expression x beta plus epsilon. And then if we remove the parentheses, we will end up with x transposed x inverted, x transposed x beta, plus x transposed x inverted, x transposed epsilon. And we see here that we multiply the inverse of a matrix by the same matrix, what would give us the identity matrix, and identity matrix times beta will be just equal to beta. That's why b will be equal to beta plus x transposed x inverted, x transposed epsilon. And if we put beta into the left side of the equation, we will get that b minus beta equals x transposed x inverted, x transposed epsilon. And that's how we can show that b is an unbiased estimator of beta, since if we take the expected value of this expression, it will be equivalent to the expected value of this right side of the equation. And since we make an assumption that epsilon is strictly exogenous, so it doesn't depend on the factors in the model, this one will be equal to 0, what would require that the expected value of b equals beta. So b is unbiased estimator of beta if the expected value of epsilon given x equals 0. Then if we plug this equation into this formula, we get the following thing, that E equals the identity matrix of size n minus x, x transposed x inverted, x transposed, times the epsilon. We simply derive that by substituting this expression with this expression. And then let's consider the sum of squared residuals expressed like this. We would get the following expression. E transpose D equals to this long line. But actually it can be simplified, since this matrix is called the self-annihilation matrix, since it is equal to its transpose, and if it is multiplied by itself, it will give just the same matrix. You can do this exercise. You can try to multiply term by term, and then you will see that you will end up with the same thing. So that's why this expression with the self-annihilation matrix will look like this. Epsilon transpose, and then in the parentheses we have the identity matrix of size n minus x times x transposed x inverted times x transposed epsilon. Then if we take the expected value of E transpose D, it will look like this. Then we will make a couple of assumptions. We presuppose that the expected value of epsilon sub I, epsilon sub j equals 0 for all I not equal to j, what means that's the absence of correlation between the errors. And we also presuppose that the expected value of epsilon squared sub I equals sigma squared for all I. So the variance of errors stays always constant. And under these assumptions, we derive the following conclusion. If we take a look at this matrix, and we denote for the sake of simplicity this matrix as capital A, then the result of this matrix product would be just the sum of these elements, where A sub ij will be corresponding element from the matrix A. And if we take the expected value for the sum of these elements, it would be the equivalent of taking the sum of expected values for each of the entries of the matrix. Since we presuppose that there is no correlation for epsilons with different subscripts, all the non-diagonal elements will be equal to 0, and we can cancel them out. And since we also presupposed that the expected value of the epsilon squared will be equal to sigma squared for all subscripts of epsilon, then all these terms, the expected values of all these terms, will be equal to sigma squared. That's why we are interested in the following expression, that the expected value of E transpose E will be equal to sigma squared times the trace of this matrix, which is the sum of the diagonal elements of the matrix. Hence, we do the quick recap on the properties of the trace function in linear algebra. Trace of A plus B equals to trace of A plus trace of B, and trace of AB is equal to trace for BA. Using these properties, we can simplify this expression and get the following form. The expected value of E transpose E will be equal to sigma squared times the trace for this identity matrix, and then minus the trace of another identity matrix of size n plus 1, Why is it so? Because you see, if we presuppose that this is matrix A and this is matrix B, then we can put this matrix A here, and then it will be the identity matrix of size m plus 1. And since the trace of the identity matrix is equal to its size, it will be n minus m minus 1. So that's how we get that the expected value for E transpose E equals to sigma squared times n minus m minus 1. And from this expression, we easily get that the expected value of E transpose E divided by n minus m minus 1, where the m is the number of the factors in the model, equals sigma squared. And this, what we have in the parentheses, is the unbiased estimator of the variance of errors, since its expected value equals to the variance of errors. Since we cannot find the expected value, we use just the estimator, and this estimator is usually denoted as s squared and looks like this. S squared equals E transpose E divided by n minus m minus 1. And this is how we compute the expected variance of errors, the unbiased estimator of the variance of errors for our model, which gives us an idea of what the uncertainty about our forecast can be. That's all for now. Thank you for watching. Goodbye.